presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I want to welcome you onto the stream here today. We're going to be having ourselves some fun talking about something called recursion. So before I get into that, there's just a few things I want to make sure I mention. First, if you enjoy what you're seeing so far, make sure you follow or subscribe and tell your friends to come on out and join the fun. I do keep in mind that you can hang on out in the chat. Feel free to post whatever you like if you want to have some fun. And of course, you're welcome to ask questions. If it's something that's a little bit more difficult for me to answer on the spot, I will hold off until I'm done the example or discussion point. So, other than that, I just have to mention, if you'd like to support this work beyond that, I do have a Patreon with all sorts of different rewards, including getting access to the notes after today's lecture. So if you wanted to get access to, say, the recursion notes for today, they'll be available over there at patreon.com/pagewizard. All the links are in the description or on the channel page, okay? So you can check that out. Makes an excellent Christmas gift if you have, say, a budding computer science enthusiast, or say you're a computer science student, you're looking for something to enhance your learning beyond where you're at, or say you're interested in computer science, you want to learn more about computer science. Excellent idea. Again, like I said there, you can add all sorts of perks, such as we have polls over there, we have a Discord server, we got all sorts of other fun nitty-gritty little details. In fact, you can even recommend topics that I talk about here. So keep in mind that there's all sorts of fun things, and of course, expect content to come out regularly, as I have been doing for quite some number of time. I guess for a number, it's been at least a couple months now that I've been putting out at least 3 to 5 videos every week, which is quite intense. So I hope you appreciate the hard work I put in on this stuff. I know I enjoy it, so hopefully you enjoy the content as well. So other than that, I'm just going to take a quick peek at 1 or 2 things before we get into everything here today. But let me know in the chat how you're doing today. Hope you're having a beautiful day so far. Today's a bit of a fun, I consider this a pretty fun topic. It also is somewhat notorious as difficult for some students to understand. So I'm hoping I can kind of dispel it and make it a little easier to understand. So you might be asking, Dan, what are we going to talk about here today? So before I get kind of deeply into this part, I just want to give you an overview, because recursion in itself, it can be a fairly deep topic. There's all sorts of different ways you can think about recursion. There's all sorts of different models for thinking about recursion. Heck, there's different ways of thinking about functions themselves as so-called recursive functions. And these recursive functions could characterize all sorts of stuff, and it's not going to be related to what we're going to talk about here today. But there's whole other branch of talking about this sort of stuff. What I'll be talking about here are the basics of a concept called recursion, and we're gonna, after that, as we're going through, we're gonna see some examples. I'm gonna keep it rather high level. We're gonna see some examples of recursive algorithms. We'll see it in contrast to something called iteration, which a lot of programmers or people that are just first learning how to solve problems might think about how you might tackle a problem, just so that you can see a couple different ways you can view solving the same problem. So we're going to do that. In addition, we're also going to learn a little bit more about, on a computer, how, we're going to keep this high level. We're not going to go into deep hardware or something like that. We don't need to go that deep. But functionally, how recursion works on a computer. So for example, if you were to take one of our algorithms and you implement it on a computer, how exactly does the mathy stuff, the dreaded M word, how exactly does that work when it comes to when you put it on a computer? And how exactly does the computer kind of replicate the M word version of how you might execute these things? because we want to have something that is functionally capable of doing what we're describing. And quite naturally, you could find that in how in programming functions or methods work in different programming languages. So we'll talk about that in respect to another kind of data structure called a stack, which we'll talk about as well a little bit here. We're not going to go full-blown into stacks, but I'll expect you to have some intuition of how a stack works. But I'll talk a little bit about that when we get there. And finally, we'll give some treatment to analyzing so imagine I give you a complexity function, and it takes the form of what we call a recurrence relation. That means that it will be described as a function, but the function will have in itself, it's described in terms of the same named function. So you'll see what I'm talking about when we get there, but also I would like to have some way of simplifying this down so that I could talk about it in terms of big O notation. So we'll see a very basic technique called iteration or iterative substitution that will allow us to break it down and try to make a good estimated guess, a good guess of what that will look like. And I'll show you how you can check it afterwards. So that's kind of a game plan for today. And of course, if you have any questions or you want to add anything to the discussion about the topic, please don't hesitate to bring her on up. We'll have ourselves a fun chat about it. I always think it's important that we have kind of all of our stuff together, all together. I don't see it really as myself just spouting things at you. What matters to me is that we kind of do this all together. So that at the end of the day, it isn't just me talking to you, it's actually a whole discussion among all of us. So hopefully you appreciate that. It's not me just kind of sitting here just saying, yeah, look, this is how it is and all that stuff. That's not really the point of why I'm here. My point here is, of course, as an educator, is to try to get you excited about computer science so that you can pursue and study it yourself as well. Get you excited about this stuff. So my point is that we're going to have ourselves some fun here today. So anyways, I thought a good place for us to start is talk about the basics of recursion. So recursion, in kind of a high-level description, is a way of defining a function in terms of itself. So in programming, we have this concept called a function. So for example, some programming languages, you'll describe all your operations enclosed within a function. Say you might know of the main function, say if we're talking about C or C++. You might be talking about inside of a class, such as having the main method, such as in Java. These are just some basic examples of functions and methods, or member functions, however you'd like to characterize these and however you would like to enclose them. But they all have names and they have parameters to them. They also may return some value. So in programming, the way recursion functionally operates is that you call a function that is the same function. So it has the same name. It may have the same parameters. But the point is that you're taking a problem and you're solving a smaller aspect of the same problem instance. Just in the same way that when I carry out this process of solving the problem, I take the problem, I break it into a smaller chunk, and I call the function on the smaller chunk to proceed and incrementally solve the problem. So in some sense, it's kind of like passing the buck on to somebody else to finish working on it for you. So we'll see some examples of what I'm talking about here in a bit. Now, in terms of problem solving, which is I would argue is probably one of the most important elements of this, is thinking recursively about a problem gives you kind of a natural way sometimes to describe algorithms. So this is in contrast to talking about, say, describing an algorithm, what we call iteratively, that is using, say, for example, for loops, while loops. Imagine you're traversing through some collection of some sort. The idea is that in those cases, you examine each member of that collection, one after the other. You may not think about things in the same way if you think about them recursively. And there's a lot of structures that are actually defined recursively, such as trees. Trees are a naturally recursive structure. So very often you'll find that algorithms that possess the structure of a tree, which many algorithms do, or many data structures that use the structure literally of a tree. I'm not talking about the trees outside that you look, they kind of go up like this. We're talking about the ones that in computer science we call, they're a type of data structure or families of data structures that have a root, and they're what we call rooted trees, and they grow downwards. That's at least how we like to draw them very often. But in such cases, it's quite natural to describe algorithms recursively, and we use this idea of recursion to do this. And what we call an algorithm that employs recursion, we call it a recursive algorithm. So just to make it clear why we might be like, Dan, why would you describe it like this if it's so darn natural? Is very often these algorithms are simpler to describe. So I'll say simple, often to describe. So just as a quick example, at some point I've talked about binary search. Now there's at least a couple different ways you could write out binary search. There's an iterative way for which you can imagine you have a while loop, and you adjust two lower and upper parameters to nudge them closer and closer by having a subarray that you're examining over, and you always make a guess in the middle of that every time you nudge over one of the lower or upper parameters, and you keep repeatedly doing this until you find a match. Otherwise, you keep incrementally making the subarray smaller and smaller and smaller, which is characterized by these two variables, usually the lower bound and upper bound, something they called L and U in the algorithm, or upper and lower. And you know when you don't run into that element when these two cross over each other, meaning that the interval crosses. Now, you can describe the same thing using recursion by simply having it where you apply recursive calls instead, where the lower and upper parts, instead of them being simulated by these L and U variables, you instead have parameters in your recursive algorithm that you adjust if you want to examine the left half or the right half. So we're going to see much simpler examples than just this, but I feel like I need to mention that there's many algorithms out there that you could describe them recursively or you could describe them iteratively. So what is the structure of a recursive algorithm? So very often they take a specific form, and I think it's really helpful to think about it in a way like this. Because remember, when we're going to be trying to define a function in terms of itself, or equivalently, we're talking about an algorithm for which parts of the algorithm call upon recursively itself. And we're going to see how this works carefully, okay? So recursive algorithms consist of two parts. So keep in mind, this is just meant to be an overall structural plan for how you might consider a recursive algorithm. It's a good kind of, I would argue, like construction plan for a recursive algorithm if you're designing a program that uses recursion or you're coming up with a recursive algorithm. These are two natural ways of composing them. So the first one, sometimes this is the trickiest part, is the recursive case. I must stress that you can have more than one of these cases, but the point is that there's a recursive case. This is where you have a solution. So when you attempt to solve in the recursive case, what happens is a solution is expressed in terms of solving a smaller, and I use quotation marks around smaller, okay? A smaller version of the problem. A smaller version of the problem. And just to clarify what exactly that means, because we would like to be able to say, I've solved a bit of the problem, but I want to pass the buck on to somebody else that knows how to solve the problem, right? So very naturally, this recursive case, what it'll do is it'll take your solution, it solves a bit of it, and then it passes it along to somebody else to handle it. Usually this is what we call the recursive call. So, which is then solved via a recursive call. So when I say recursive call, I'm talking about when you call the subroutine or call the function again with among, remember, we're describing things in terms of ourselves. So we haven't really seen any examples of this, so please just hang on very closely. We're going to walk through this carefully. A recursive call on the smaller input. So we have this recursive case. So this is the one that's going to call, or these are going to be the situations where you call the algorithm on of itself, right? You're going to solve a smaller version of the problem. Then the other part is when you know how to solve the problem directly. The base case, and you may have multiple base cases. So a way to solve the problem is presented. Is presented without reference to itself. So there's no recursive calls here. So I must stress that the problem that we're talking about is a sufficiently small one. So for example, it may be the case that you know how to solve the problem when you only have, say, one element to consider. Or you may know how to solve the problem when you have a small enough sized input. Or it may be the case, for example, say if we're talking about something quite practical, it could be the case that there's an algorithm for which you could describe it recursively, but when the input gets small enough, what you're examining, you might want to use a different algorithm that you know how to solve that problem directly. So this actually quite often happens when you take and combine sorting algorithms. You take this big complicated input, a very big long one, and then you may break it into smaller chunks, but when they're really small, they might be really easy to solve directly. So that's another way you can view the base case. So very often it's helpful to think of recursive algorithms into these two pieces, and identifying these two parts can be very helpful in thinking about how it's actually solving the problem, if it does. Because remember, I could give you an algorithm, it may not work correctly, but I need some way of thinking about that. Now, it doesn't have to be where you have to think about, oh, I do this and I break it down to a smaller and smaller and smaller case until I get to the base case, which is one natural way of thinking about it. There's types of algorithms called divide and conquer algorithms that do something like this, where what it does is it takes the problem, subdivides it into smaller pieces, and keep in mind, each one of these recursive calls will keep repeatedly passing the buck on to somebody else to solve the problem until it's sufficiently small, and you may solve that one directly. That's where the base case kicks in. So then you solve each one of the smaller pieces. The point is there's still a conquer part for which it combines all of these answers to get an answer to the overall problem. That's why it's called divide and conquer. But it has a different, not every recursive algorithm takes on this form. For example, it also could be the case that you begin at the base case and you keep repeatedly applying the recursive case to build up an answer. So that's another way you might think about this. So you can think of this like you start at the top. You think a very top-down way of thinking about recursion. You imagine you have the whole problem, you break it to, you take a piece of it, take that and combine it with whatever answer you get from a recursive call or multiple recursive calls until you get down to the base case. So very top-down way of thinking about it. It's very classical for recursion to think about it like that. But you could also think about it the other way around. So sometimes you could have it where you begin at the bottom at, say, the base case and build up to the answer by repeatedly applying the recursive case. In fact, that's a very natural way of thinking about recursion versus iteration. It's that you imagine you can examine each one of these, but instead of imagining you apply this definition recursively, you may know how to directly solve it. That's where iteration would differ from recursion. So So just keep in mind that you can think about this from a top-down kind of process or a bottom-up process. So I thought it would be a good idea I start off with something fairly basic, but I think it also was rather helpful. So let's start off with a pretty cute example, and it's something you could do with your friends. We're going to consider the example of counting. And in particular, we're going to talk about counting our friends. So let's talk about thinking recursively. So let's consider this example where we're going to counting our friends. So here's a scenario. Here's a scenario, just like I have over here. Imagine you have your friends lined up so that you're able to count them all. So suppose you ask your friends to line up. So they're right beside each other, kind of like what I have right behind me. See, the behind me is over here. So, I'm having way too much fun with this. Suppose you ask your friends to line up. How many friends do you have? Now, there's at least a couple different ways you might approach this. Now, before we get thinking about this recursively, I thought we would just see the contrast this, how we might approach this iteratively. Does anybody have any suggestions for how we might approach solving this problem iteratively? So just as a reminder, iteratively simply means I have access to all my friends here, and I'm going to use the idea of examining, say, each member of my collection, whether this be through for loops or while loops, those types of structures, those types of control structures. So how might you go about this iteratively? Are there any suggestions? Well, if there aren't any suggestions, I'm going to kind of lead you in one direction here to think about. Well, imagine I'm here, and I don't know, I'm doing some tally work. I got myself a, let me see, I got myself my notes here, but I also have a tally. I could take a tally on my notes. Well, what I could do, akin to something along these lines, I can imagine I can line up my friends like this, right? I could I can iterate over each one of my friends, and I can count up how many there are, how many friends I have. So I could go over here and I could just examine each one of these, and I can put a tick on my piece of paper and keep a running total of how many friends I've tallied up. So this is how you might solve this problem iteratively. And whatever you get at the end, after you tallied up your running total here, when you have your whole running total, you return that number. See, it's pretty natural, right? So you just count through all your friends. Tallying up how many you have found. And return the total count. Right? That seems so you can easily implement this with using for loops or while loops. So that's one way you could solve this problem. So imagine I give you line up some group of friends and I want to count them up. I can do this, right? With a sufficient amount of paper, I could most certainly accomplish this. Now, let's think about this recursively now. Let's think about this recursively. So, I want to come up with a process for which I can determine how many friends I have among all my friends. See, I've got my dinosaur friend. Oh yeah, and I also have another dinosaur friend, but this dinosaur friend's is much brighter green. I like that. I love all my dinosaur friends. I love even my Ninja Turtle friend and my cowboy friend. Love all my friends. So, what I would want to consider is some process for which I could potentially delegate the task of tallying up to my friends so that I can get a total number of how many friends I have. Well, I want you to think back, and maybe you experienced this in school. I know I did, but in grade school. But you most certainly could try an idea like this. So, for example, say if you're getting a handout in class, so sometimes you're given a big stack of papers. What do you do very often? You take one and you pass it along, right? So you take one of these notes, you pass it, and then you pass along the rest. Well, maybe we can use an idea kind of like this to find out how many friends I have. Now, instead of it just simply being that I'm going to pass along the rest, maybe I might want to think about this instead like this. So, one of my friends knows, in fact, they are one of my friends, right? And they know to their right, no, this would be to their left, to your right, you see that all the rest of my friends are here, right? So if I look from here to your right, you see that I have 3 more friends, right? But likewise, from any one of these, I could ask a very similar question, right? So, for example, if I ask my cowboy friend, well, how many friends do you have to your your right, right? To this way. Well, there's me, and there's anybody that's to the right of me. Right? Right? So now we might have a nice way of thinking about this, because all I have to do is once my friend finds out how many friends that I have, including themselves, they could pass that information along back to each of their friends to your left. To your left. Until they could report it back to me. So you can even think about this like you're passing along the tally sheet to them to keep track of this information. So let me give you kind of the breakdown, then we'll walk through an example of what I'm talking about here. So we have a recursive case. So I'm going to abbreviate with rec here. A recursive case is if there is a friend to your right, ask how many friends there are. So all you have to do is return this number plus 1. And this is because you are a friend, right? The plus 1 is yourself. So, for example, suppose that I'm over here and I want to find out how many friends I've got. I'm going to start off by asking the question to my friend over here, my lovely green friend here. My lovely green friend would say, well, I can always ask to the right, my friend, how many friends there are. And whenever I get the answer back, I can just add 1 to that. So I'm going to pass that information along to my first dinosaur friend. And I could ask the dinosaur, hey, how many friends are there? Well, I can always ask my friend to the right, and when I get the answer back, I could just add 1 to it, right? So far, now I'm asking my cowboy friend, okay, well, how many friends do I have to the right? Well, the answer is simply going to be whatever I get from my friend over here, and I'm just going to add 1 to it. So I do the same thing, I get my other dinosaur friend, this Yoshi. So if I ask this dinosaur, how many friends do you have? Well, there's something interesting here. Notice that this dinosaur has no friends to the right. Do you see that? So it means that we know actually how to solve this smaller problem directly. So should I employ the recursive case again? Or should I describe this directly how to solve it? Well, do you see how when our recursive case, I ask how many friends there are to the friend on my right, right? But I don't have a friend to my right, so I know how to solve this directly. I just count myself, right? And I could pass. Then when my cowboy friend wants to get the answer back from my green Yoshi friend here, they know the answer, right? So naturally, we could describe this as a base case. When I don't have any friends to the right. So otherwise, we just simply return 1. And this is just for yourself, right? There are no friends left to count to the right, right? So now let's walk through this again now. So now that we've actually walked all the way over here, and our green Yoshi friend here has determined, based on how we define the base case here, does everybody see that? Is that we know there is 1 friend. The cowboy friend gets back the answer from the friend to the right. Cowboy knows that there's 1 friend to the right. Cowboy says, hey, look, that includes me. So now I have 2 friends. Now I could give it to the other dinosaur. I know, sorry guys. I'm sorry. You're the other dinosaur, okay? Now, I pass along that. Now the answer from the cowboy back to the other dinosaur. Now, there are 2 to the right of the other dinosaur. Then I just count. I guess the other dinosaur counts themselves, I guess. Him or herself. Then, now I have 3. And the Ninja Turtle now says, hey, cowabunga, guys. And I got 3 to my right, and I consider myself radical. And hence, gives back the answer to me. And the answer to me is how many? 4. So, do you see how this actually could give us information without needing to do a whole lot? Thank you so much for the raid, Tor. Welcome on in, anybody. We're having ourselves some fun here. So hopefully everyone understands the example. So we're seeing how we can count our friends recursively. So that's one example of how we can think about counting friends recursively as opposed to iteratively. So I thought it would give us another example of the same spirit as this, where we're going to try counting up numbers. So let's try this out, okay? So how's it going, Tor? How's it going, everybody? I hope you're having a beautiful day so far. We're having some fun with recursion. Now it's going good. It's going good. Now we're talking about recursion today. So I thought it would be a good idea we see another basic example so that we could get ourselves wrapped around this idea of having a recursive case and a base case and thinking about it in contrast to iteration. So let's consider another example. We'll call this summation. So consider the sum 1 plus 2 plus 3 plus all the way up to some positive integer. So that's like 1, 2, 3, 4, any number that's bigger than that. That's a whole number. N. So suppose I want to evaluate what this sum is, given n. So I would like to know that. So we can evaluate this in a couple different ways. Can somebody give me a suggestion for how I could calculate this? And I'm not looking for the clever answer. I just want to know how you'd use iteration, so for loops or while loops, to do it. Any suggestions? So suppose I wanted to calculate that. That's all. So how would you go about it? And again, I'm not looking for anything too crafty here. Just looking for something that uses for loops or a while loop. Just the general idea. Come on, guys. I know this one's easy, right? It's one of the first things you might try doing with a for loop. Well, I'll start writing, and you're gonna see how we can go about this. So I'm gonna write down let's write down some actual code that would actually do this. So suppose I have a function that's gonna return an integer, and I'm gonna call it iterative sum. And it takes in an integer n. So what I'm going to do is something quite similar to actually what I did in our last example. So I'm going to keep a running total. So I'm going to have something, a variable I'm going to call sum. So I'm going to call it int sum, and I'm going to assign it 0. And then I'm going to have my for loop. So naturally, if you actually think about it, I could go through each one of these values and add it to this running total. So here we go. So I can go for int I is assigned 1. I is less than or equal to n. I plus plus. So I'm going to increment I. And then all I have to do is I could just assign sum to be sum plus whatever the value is, right? Because this will go through. So I really just need something just this basic. So notice every time I takes on each one of these values, and I'm just going to keep it included into my running total, right? And I can simply return the running total when I'm done. It should remind you a lot of our example of counting up our friends iteratively. So I'm sure this is what you were thinking about when I was talking about iteration. Did I get anybody's guess? But yeah, you could put this, for example, into something like C++ or Java. Say if you're using if this is just a method, it's not a static one, but this will certainly, you could pump into something like C++ and check her out. So now let's think about this in a different way. So this is how you might approach this iteratively. How might we think about this recursively? And I want you to think back to our previous example. And oh no, I knocked Yoshi over. I'm a monster, everybody. See, our Yoshi friend, I'm going to make sure I put Yoshi over here. So let's think about this in a somewhat different way, okay, everybody? So remember, in our example where we're counting our friends, remember I looked and I said, hey, look, if there's a friend to your right, increment it always by 1, and then it's how many friends you got to your right. Well, we can do something kind of like that here too, right? Well, let's think about this now. So we can think about summing n integers recursively. So let's think recursively. So I want to think about this now from imagine. So you know how I wrote 1 plus 2 plus 3 plus 4 plus 5 all the way up to plus n, right? Imagine I start off at n. So let's start. And I must stress you don't have to do it this way. I just want to show you an example for which I start at kind of like what you would imagine is at the end process as opposed to beginning. So start at n. Then, do you notice that if ever I wanted the answer to that total sum, it's the same as me saying, you imagine you start with n, then add to it everything else. So n minus 1 plus n minus 2 plus all the way down to 1. Right? So you'd agree with me that this, if I added these two things, I get 1 plus 2 plus 3 plus 4 all the way to plus n, right? The thing is, I just don't know how to do this. Okay, if I'm clever enough, most certainly I do, but I could show you how you could think about this recursively by passing the buck on to somebody else, whom will eventually get an answer to the question of how to add them all up. Well, think about it. Well, what's this? What's that? Let's continue this process. So this is just simply n minus 1 plus n minus 2 plus n minus 3 plus all the way down to 1, right? Pretty interesting, right? So notice that now I have a way of thinking about this by decomposing my problem instance into smaller chunks like this, where what I'm doing is I could imagine I have like a total of how many I currently have, but notice that if ever I want the answer to all of it, I can always break this down into a smaller piece and pass the rest on to get added, namely this part, just like this part. And I can keep doing this. So I can have n minus 2 plus what would go right here? Well, it would be n minus 3 plus all the way down to 1, right? And you can imagine eventually you're going to hit 1. Eventually you're going to get 1. So eventually you're going to have it where you're just going to have whatever the answer is just going to be 1. Right? It's eventually going to get there. So this gives us an interesting case to think about here. So we know how to actually answer the question by performing what we call the recursive call. So whatever the answer is, for example, here is n plus whatever the answer is to that. What's the answer to this? Well, it's this plus the answer to that. Well, this is another recursive call, right? Well, what's the answer to that? Well, it's this plus all of that. Well, you can keep doing this over and over again until I eventually only have 1 to add. So this should remind you a little bit about how I pass the buck on to somebody else. Namely, like on my friends, I always would ask my friend to the right. In the same way, I'm just passing the rest of this off to, you can imagine these each number like a friend. It's a friendly, good old time, right? So here's how you might approach this now. So you can imagine I'm going to write it again in code. So you can actually see this as code. So you got rec sum. And you imagine I take in an integer n. So I must stress that n is a positive integer. And remember, when I write this out, I want to identify the base case, or if I have multiple cases, multiple base cases. So it's usually good practice to identify and comment these specifically, so that way it's helpful for the reader. You don't want them half guessing what you're up to, okay? You want things to be clear. That's why we would like to have clear ideas when we're thinking about this stuff. So if n is equal to 1, you know the answer to that is 1, right? So this is your base case right here, just like I have over here. You know the answer here is 1. So here, you're just going to return 1, right? Right, everybody? We know the answer to that. Okay. Otherwise, this is our recursive case, and this should remind you of what we got over here. So remember, what I said was, hey, look, whatever I have the number, and I add to it the rest of the sum. So what exactly am I saying when I do this? When n is bigger than 1? Well, it's n, whatever that is, right? So we're going to, the answer, as we said, so I'm going to return whatever that is. It's going to be n plus, how do I write down, add up all the rest of the numbers that are smaller than my number? How do I write that down? Now this is where the recursion part of this, how I said, remember I talked about this idea of having it where we use the same name of the function and we're just calling it on a smaller input. A smaller input, or you can visualize or figuratively imagine you're taking, I guess the better word would be conceptual breakdown of the problem into a smaller piece. So it doesn't have to be literally a chunk that's smaller, it just has to be that we're taking and solving a smaller problem. Smaller. We never want to have it where we're just trying to solve the same thing over and over again. You'll find that we'll run into a lot of problems if we start trying to do that. We're not actually incrementally improving our solution here. We're not trying to solve the problem in that case. We're just going to keep trying to solve the same thing over and over again. So this is where you're going to get your recursive call, everybody. So here, I'll just go, this is where I'm going to call recsum. So please note that that's also the name of this function or method. So what would I write right here? What would I write inside here? What would I write there? What's going in the parameters here? There's only one, but what's going to go in there? So remember, I take whatever the number is, and then I want to add up the rest of the numbers that are smaller than it. But how would I describe that recursively? So think back to our example with our friends. We'd ask the question to our friend to the right, and for which they would give you an answer. But let's keep this now specifically to discussing this function. So I'll give you a hint. It won't be n right here, because that will mean we're trying to solve the same problem again. We want to solve a smaller problem. But what does the smaller problem look like? Well, what's the big, so what, to solve this, well, what is that? So that's us adding 1 plus 2 plus 3 plus 4 all the way up to n minus 1 as opposed to n. So it's one less number. So right here, this is where you would have n minus 1. This is our recursive case. And naturally, that completes the function here. So this is actually a recursive way of solving the same problem. So are there any questions at all about our example here? So you might be staring at this a little like gawk-eyed about this, because there's a couple interesting things happening here, namely, well, there's no other variables right now other than, okay, there's n that gets passed along. There's this function call that has the same name, but don't let that throw you off. It's still a function call. It's just like any other function call. It just has the same name and the same parameters. Just the inputs to those parameters are different. They're smaller. So one thing, actually, let me just show you an example of us going through this example here. So suppose that I wanted to go, say if I wanted n as 5. So if I put in n as 5, this would say that to get the answer to this, I would go 5. Remember, this is 1 plus 2 plus 3 plus 4 plus 5, right? So how exactly would I do that? Well, according to this, what I would do is do the following. I would do 5 plus, well, the recursive call would be answering the following question. 4 plus 3 plus 2 plus 1. So that's what rec sum n minus 1 would be. So this is what rec sum 4 is. So we now take rec sum 4, and to answer this question, we have to answer rec sum 4, which this is 4 plus whatever rec sum 3 is, right? But what's the answer to that? Well, the answer to this is 3 plus rec sum 2, right? But what's the answer to that? Well, the answer to this, now remember, each one of these is a function call, so each one's going to execute this function. But it can't finish until this line can be completed, right? Just in the same sense as we're talking about the M word, the mayonnaise, why I can't just simply just say, oh, well, I'm done here. I could just, we aren't done until the computation is completed. So we got 2 plus rec sum 1. But what's rec sum 1? Well, we know the answer to that is 1, right? So we got 1 plus 2. Well, the answer to this is 3. Then we could pass that back up this way. So now we have 3 plus 3 is 6, right? 6 plus 4 is 10. And now we have 5 plus 10 is 15. So that means the answer is 15. And that should be what we expect, right? Because 1 plus 2 is 3. Then we have plus a 3 is 6. Plus 4 is 10. Then plus 5 is 15. So hopefully my arithmetic is correct, and we should get the correct output of 15 in that example. So we're going to talk more about this eventually, how this exactly works on the computer, at least at a high level. But we're going to now see another example. Are there any questions about this guy here? There's nothing too scary about this, right? Remember, it's just like our other example we had where we're counting our friends. Just the difference is now we're counting them as numbers, as opposed to it being like one atomic unit. Now each one is representative of a number. So I'll include in the notes an example where instead of thinking about these as 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to n, or thinking about it as just counting friends, you can imagine I'm given an array. And I want to go and do the same process again, but I want to sum over all of the elements in the array. So check that out. It'll be very similar to this. Just instead, it'll be indexing at these spots in the array. Oh, late night, late night. Got a late night, that's a long day. So let's head over here. We're going to do another example. Usually I find it's helpful to see a bunch of different examples, just to help you get kind of in this mindset. So right now we're looking at some rather simple examples of recursion, but it's getting used to this idea of thinking about the problems by decomposing them from one bigger problem to a smaller one, or maybe potentially smaller chunks of the problem. The point is, eventually somebody knows how to solve the problem. That's a really important step. That's why we have a base step, or base case, or multiple base cases, is we need to eventually have somebody that I pass the buck on to, namely some one of these calls has to have an answer that doesn't use recursion to solve it, okay? Otherwise, we're going to end the infinite abyss of recursively trying to answer questions we don't have answers to. So let's do another example. Let's consider what is called a factorial. Let's consider factorial. So I'm just going to define it for positive integers, though you can technically define it as well for all sorts of different other values. For any positive integer n, we're going to define define n factorial. So we usually use this exclamation mark to indicate that. So this is n factorial. So that's how you would read this. Where it's going to look like this. Now, I'm going to deliberately write n factorial in a way that is recursive. Now, if you've seen this guy before, you'll be very used to writing it like this. So you might say, well, I'll just write it off to the side. I haven't yet defined it using recursion yet, but you might be used to writing it like this. N factorial is n times n minus 1 times n minus 2 times all the way down to 2 times 1. So it's like n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. So for example, something like 4 factorial would be 4 times 3 times 2 times 1. So let me define this now recursively. So n factorial is going to be n times n minus 1 factorial. And this is if n is greater than 1. So I have a question for you. This would be what you would call the recursive case, right? Or is this a base case? Well, let me write down the second possibility here. So 1 factorial is just equal to 1. This is when we have if n is equal to 1. So which one of these two? So we have 1 or 2. Which one is the recursive case? 1 or 2? Which one's the recursive case? So remember, the recursive case is where it provides you a solution for which it requires, to answer the question, a recursive call on a smaller part of the problem. So it may take a part of the answer, but it passes along the rest of the answer to you want to get the answer for some smaller part of it. Sorry, I'm getting really excited here. I'm just anticipating an answer here. So is it 1 or 2 for the recursive case? Well, it's 1. It's 1, right? So 1 is the recursive case. And 2 is a base case. And I must stress that you can have more base cases. For example, if I wanted to define what 2 factorial is, to be 2, that's another base case I could define if I wanted to, if n was equal to 2. Just as an example. So just to reiterate what I had said previously, well, for factorial, you can think of it like this recursively. It's 4 times 3 factorial, right? But to know the answer to 3 factorial, well, what is that? Well, the recursive case says, well, because remember, I just applied the recursive definition of what n factorial is because n is greater than 1, right? So what I've written actually on the board here is actually what we would call a recurrence relation. So this is one way you could also describe things recursively. So in this case, it's literally talking about functions from the M word, the mustard. Well, to answer this question, well, this is just 3. Well, 3 factorial. This is just 3 based on the recursive case. It says it's 3 times 2 factorial, right? Well, to answer this question, well, that's 2 factorial is equal, because it's still the recursive case we would apply because n is bigger than 1. Well, this is 2 times 1 factorial, right? Well, now I do my call here. And you see, okay, well, 1 factorial is just equal to 1, right? This is our base case right here. I know the answer, right? For 1 factorial is 1. So now, because I know the answer is 1, I can work back to answer each one of the questions, right? Each question being a recursive call. So now I know the answer to this is 1. So this is 1. So 2 times 1 is 2, right? So this is 2. Well, 3 times 2, well, that's 6, right? So to answer 3 factorial, it's 6. And 4 times 6 is what? It's 24. So this is... The point is that every time I get one of the answers, I can pass it along to answer the question for each one of these. So notice that I break the problem down in this case to a smaller and smaller and smaller example until eventually I know exactly how to directly answer it, right? And then once I have that answer, I can pass that along just like when I was talking about adding those numbers from 1 to n. Notice it's quite similar. It's actually quite similar, right? It's just like it, except now we're just multiplying, right? Now we've called it also factorial. So let's write down what this would look like as an algorithm. So I'm going to write this one a little different. So this time instead of writing just code, I'll write this as pseudocode. Just so you can see how we're kind of building up to different ways we could describe a recursive algorithm. So far we've seen how we can write it as an actual part of a program. And now, let's write down what this algorithm would look like. So just before anything, to perform this iteratively, you just use a for loop quite similar to actually how we did for our sum example, right? Except now you'd just be multiplying instead. You start off at n, you just keep multiplying by each successive one downwards or upwards, depending on how you set it up. If you want to start at n, you work your way down, but you decrement what I would be. As opposed to starting at 1, you would increment I, but you would multiply instead of adding. So let's describe an algorithm here. We're going to call the algorithm fact. And it takes an n. N is going to be a positive integer. Now, to keep this simple, I'm also going to make it so it works also when it's non-negative. So we defined it over there for being, we defined it for positive integers. I'll allow it to be non-negative here just because I know somebody's like, well, 0 factorial is equal to 1. Well, why can't you just simply include that? So I'll just add it in there just as an extra flex, okay? So, and the output is going to be n factorial. And I'm going to note for you that 0 factorial is equal to 1. So if n is bigger than 1 or strictly larger than 1, then, so as we described earlier, so notice I'm just translating the recurrence relation into an algorithm in this case. Some cases it's not very straightforward how to do that. In this case it's really easy. So if n is greater than 1, then we have our recursive case. So here, we have that. Otherwise, we're going to have the base case, right? I haven't put anything in here. We're going to figure that out. We know for the base case, we're just going to return 1. That's what we've established already, right? Well, what's going to go right here, though? What's going right here? Well, to answer the question of what n factorial is, recursively, we said what? We said what about it? So let's head over here. So what did we say, everybody? The recursive definition here was that n factorial is equal to n times n minus 1 factorial. So, what should go right here then? And remember, the answer to n minus 1 factorial is going to be described in terms of our algorithm's call to fact. So you know it's going to be whatever the number is times, well, the answer to n minus 1 factorial would be calling fact on what? N minus 1. And that's it. So notice it's very simple. One thing that's rather deceptive at first is the fact that you don't see loops or anything like that. It's because of the way recursion works in this case. And you'll find that if you walk through an example like this, you might find that it will actually remind you a lot of if you took its iterative counterpart using a for loop. If you took it one step at a time, just there's a mechanism underneath this that, just similar to actually our example we did before, that is going to keep repeatedly trying to solve a smaller and smaller problem. So that's why each one of these calls corresponds to something else, which we're going to talk about. So, just as a remark about iteration versus recursion, and I must stress that the versus is rather superficial. You shouldn't see these as competing paradigms. They're things that you should consider being things that you might consider in both ways. You may have an algorithm that uses both. So for example, you may have a base case that maybe uses iteration, but it's only because it's a sufficient size that is easy enough for you to solve it directly. That's one way you might use a base case, but you'll find very often in divide and conquer algorithms that the size of the input will become something that is small and constant in size. But in practice, you might find some way of kind of trading off between a recursive version of the algorithm versus its iterative counterpart, or using a different algorithm that's iterative, as I discussed before. So you can view recursion like an alternative to iteration. So don't look at it like there's one exclusive tool in town here. The point is that if you have a recursive algorithm, you could write that using iteration and vice versa. However, I must stress, it must be stressed, that iterative algorithms based on recursive algorithms may not translate naturally. And I'm using that rather subjectively, and vice versa. So just to reiterate my point, if I give you a recursive algorithm, there's going to be an iterative counterpart to it, but to create that, it may be nice and simple, such as some of these examples over here. You can see very natural ways to rewrite that using a for loop or a while loop. But for some sufficiently complicated recursive algorithms that rely on the recursive structure of some underlying mathematical object, such as like a tree or anything like that, you may find that it's not quite as simple as just simply replacing things with for loops or while loops. You may actually have to simulate the recursion. So just keep that in mind. So I want to give you another example, just because we've seen always ones with one recursive call. And I just want to show you that it doesn't have to look like that. So let's do another example. So I thought I would dip into another classic. Let's consider the Fibonacci numbers. Another classic example. So let's consider Fibonacci numbers. This is a really well-known number sequence. There's several different ways you can define the Fibonacci numbers. So it's a well-known sequence of numbers, and it works like this. So we're going to define fib of n to be fib of n minus 1 plus fib of n minus 2 if n is greater than 2. And we're going to have fib of 1 equal 1 and fib of 2 equal 1. So just as an example, just so that you can see how this works a little bit, is let's start off with, so we have the first two Fibonacci numbers here. Now I must stress that you could also define it where the first Fibonacci number is a 0, but we're going to keep it like this. So we would have 1, that's the first Fibonacci number. This next one is 1, right? That's what fib of 2 is. How do we compute fib of 3? Well, yeah, all you do is fib of 3, so it says fib of 3 is equal to fib of 2 plus fib of 1, right? So it's 1 plus 1, which is equal to 2. So that's the third Fibonacci number. How about fib of 4? Fib of 4, it says that that is fib of 3 plus fib of 2, right? So that's 3. How about the next one? Well, fib of 5 would be fib of 4 plus fib of 3, right? What's happening? What's happening? Just keep it very simple. When I look at this 5, it was always because I added the two previous Fibonacci numbers. So if 2 plus 3 is 5, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. And you can keep this process going as long as you like. So let's write down this as an algorithm with pseudocode. And you'll see that this is actually not too terribly scary, right? Because we have a recursive definition of Fibonacci here. So we got our algorithm. We're going to call it fib. And we're going to take in a positive integer. And it's going to compute the nth Fibonacci number. So, what's a good place for us to start for describing the algorithm? Well, a very natural place would be to start at the base case here. You don't have to go with the base case first. You might write the recursive case first. I'm just going to describe with the base case just to show you that it doesn't have to be recursive, base case, or the other way around, as long as you're careful with your control structures. So if n is less than or equal to 2, then we know the answer to the question, right? Fib 1 and fib 2 are both 1. So I'm just going to return 1 in this case. So if n is less than or equal to 2, we just return 1, right? Piece of cake. That's your base case. Otherwise, we have the recursive case. And how do we answer that question? Well, we're going to return the answer to the question. Well, the recursive definition says you add this one to that one. So let's just do that here. Fib of n minus 1 plus fib of n minus 2. And there we go. That's it. So notice that you don't just have one, you can have many recursive cases, and many recursive calls that might happen. Just you don't want to have too many because then it gets a little difficult to know which one is doing which, unless you have a very specific and exact way for which that is occurring, like this. However, I must warn you that when you do things like this, to calculate out the nth Fibonacci number using this recursive algorithm, I gotta show you how this plays out. So remember that the order of these calls may matter for which one finishes first out of these two recursive calls. But the point is to get the answer of fib of 5. To get that answer, you need fib of 4. And you need fib of 3, right? But to get the answer to each one of these, I have this one, I need the answer of fib of 3. And this one, I need the fib of 2, right? To get the answer to fib of 3, I need the answers of fib of 2 and the answer of a fib of 1. Well, the answer to fib of 2 we already know, right? That's just 1. But you can do the same thing, because notice that fib of 2, that's just 1. Fib of 1, that's just 1. You can get the answer for this one right here. But do you notice now that because we have more recursive calls, in fact, we have several that may potentially occur here, which I want to mention something about. But let me just finish writing out what some people would refer to this as a call tree. So notice every single time I'm showing you each one of the function calls for our algorithm. So does each one of them. That's the initial call. Each one of these is a call on fib. So in this case, we have fib of 2 and fib of 1. So this is what you would have to calculate to get fib of 5. So notice how many function calls I have here. You might ask, Dan, how many at most are there here? Well, notice here that every single time you have 2 calls at most, right? Each one of these, you have 2 calls at most. But notice that it actually skews that direction. So notice it's more heavy in that direction, the number of calls that happen. But notice every single one of these does at most 2, right? So for example, here, I have, to get fib of 5, I do at most 2 calls, right? In fact, there's at most 1 function call you could argue this is kind of like this is a tree-like structure. In fact, it is a tree. You have 1 function call here. On this level, you can see there's at most 2. Here, there's at most 4, right? If this were to continue to expand, even though there aren't any down here on this rightmost side, do you notice that there could be no more than 8, right? Do you see that this call tree, the number of calls that are occurring is growing exponentially? So naturally, you might ask, Dan, what does the running time of this recursive algorithm look like? It's not pretty. It's not pretty. This runs in exponential time. So this is actually an example for where you might want to consider iteration as opposed to recursion. In practice, at least, or at least to speed up this algorithm, instead of us redoing a lot of that work over there, instead keep track of that information in, say, an array, and look up if you have the answer already, just like I had my list over here. Say if I already knew what fib of 3 was, rather than recalculating it again, let's just look it up in a table. Then that saves me from having to expand out this whole right side here. I can just get the answer right here. If I knew what fib of 3 is, if I already calculated it over here. You see what I mean? I'll let you think about that. That actually brings to a concept called dynamic programming, which I won't discuss here. But the point I'm getting at is that recursion, although it can make algorithms look really nice and pretty like this, it also may have drawbacks. So you have to think carefully about what the algorithm's doing when you describe it like this. Just like if we're talking about iteration, it may be a really ugly looking algorithm, but it might be faster. I'm not quite sure. It depends on the circumstance. But yeah, that's the basics of recursion. So hopefully you found these examples pretty helpful. So any questions? Any questions at all, anybody? Any questions? But don't be shy. I'm happy to answer any questions. So I'm just going to erase the board. Well, in case there's anybody has any questions, feel free to put it in the chat. So what we're going to do next, actually, after this, if there's anybody has any questions, we're going to talk a little bit about how recursion works. Because you may have looked at some of my examples here and be like, okay, well, how do you know, like, how does like the function get the answer once I've requested, like, so when I asked my friend, for example, how many friends they had, like how many friends I had that are to the right, well, how does like a computer program maintain this information? That's something that is it's a completely valid question. And mathematically, it's easy to conceptualize, but like, what does that look like? Like, how does it function? Like, I'm not trying to come up with a pun. I literally mean, like, well, like how does that function? Like, how does it actually calculate that out? Like, how do you know to return back to the computer program for which you're waiting for the answer? Like, how do you do that? So that's actually what we're going to talk about next. And to do that, it relies on me talking about the idea of our call stack, which is something, if you've talked a little bit about functions before, you may have heard of this concept before. If not, I'm going to talk about it here. I'm just going to move a few of my friends around. A few of my friends are going to move around a little bit. I just want to make sure I'm not taking up too much space with everything. So I'm just going to move some of my bins. Okay. So one thing I just wanted to mention, just again, is if you're looking for another example of how to recursively add the elements in an array, I have included an example of a full Java program that you can check out. It's going to be in the notes. I'll be available after this live lecture. So I'll post it there on Patreon, patreon.com/pagewizard. So again, if you're looking for a good Christmas gift for somebody, or you're interested in computer science, you want to get yourself a little gift, so the entry is very low bar. It's a very low bar to enter to get these resources so that you can help you learn computer science, which I'm always happy to help out with. Okay. It looks like we don't have any questions, so I think we're going to proceed here. So let me just check one quick detail here before I get too into things. Let me just check one quick detail. Okay. Okay. So let's get to our next part of our lesson. So next we're going to talk, so previously we talked about the basics of recursion. We talked about some of the fundamentals and some ways of thinking about problem solving recursively. So namely, we had things like the recursive case, the base case, and we talked about how we could do things like adding numbers, how we could compute factorial or Fibonacci numbers using recursion. And we've seen some examples of programs or even algorithms written in pseudocode for doing such things. And we sort of made a presumption about how it works. So now I got to talk about how it works. So how does it work? That's a very good question. How does it work? So recursion relies on the call stack. So if you've never heard of this idea of a call stack, we're going to see an example of what I'm talking about in a moment. I'm not going to go overly technical about all of the parameters one of the records or activation records or stack frames or call frames, what would look like. I'm just going to keep it higher level here. This is sometimes also called the runtime stack. And you might ask, Dan, what the heck is this thing? The call stack is used to store data. That R's looking a little sad there. To store data needed for methods or functions while the program is running. This includes the following. So some things that are known. So this is stuff that gets stored in the so-called call stack. So things such as the parameters of calls. So I'm talking about function or method calls. They're local variables. So every one of these calls, I want to be able to keep track of the local variables associated with that call. I also want to have it so that I can keep track of the return value. And of course, I want to know a memory address for where to return to continue executing when I'm done executing my function or method. Memory address of where to return. To continue executing. So just to be very clear, whenever a function or method is called, so whenever a function or method, whichever is your favorite taste of flavor, whenever a function or method call occurs, an activation record, which is sometimes also called a stack frame, or call frame, an activation record is created, which has this information, is created and pushed onto the call stack. So I must stress that when you are executing your programs during runtime, there's going to be what we usually refer to as the heap. So you have heap memory. There's also stack memory. So this call stack is just a part of the runtime memory. So what am I talking about here is that every time you make a call or you call a function while executing a program, it goes onto this so-called call stack. So a stack, just for context for those that aren't familiar with what a stack is in data structures. So a stack, you might think of it like a stack of plates, for example. So a stack of plates may start off as empty, and then I could push plates onto the top of the stack. These might represent different objects. In this case, they would be representing activation records. So when a function finishes executing, it gets what we call popped, or it leaves the stack. So it gets popped from the stack. So it gets removed from the stack. But it only is the thing that's occurring on the top of the stack. So for example, Say at the beginning of execution, your typical programming language, you'll start off with a function or method call to some main function. And then this calls some other function. Well, that goes on, that creates an activation record. It gets pushed on the top of the stack. The reason why we have to keep track of things like the memory address toward a return is that that information helps us get back to when this function finishes executing, gets popped or leaves the stack. It tells us where to continue executing from for our function here. But it also, we could pass along the return value when we're done. So the whole idea is that every time I make a function call, it gets pushed onto the top of the call stack. This call stack will, each time when I push something to the call stack, whatever's on the top of the stack is what's currently the function executing. So please just keep that in mind. So the big thing I really want you to know about is that we can push elements onto the stack, but they always go on the top of the stack. But you can also pop elements off the stack, which get removed from the top of the stack. Everything is handled on the top. This is in contrast, by the way, to something called a queue, for which what happens is when you do end queues, it goes onto the back of the queue, just like you would be waiting in a line, hence its name, but you leave the front. So just please keep that in mind when we talk about the call stack, because it's just a stack. It's just one for these activation records. And I must stress, this isn't something special just for recursion. This is how your programs execute, is that whenever you call a function, it goes onto the call stack. Just recursion is just a special kind of function call, right? You're just calling a function with the same name, maybe different parameters. So the big thing I really want you to know about is whichever function, so this is referring to its activation record, is on the top of the stack, is actively being executed by the computer. And remember, function calls, when you're using recursion, are no different than just any old function call. Please remember that. There's nothing special when you start thinking about it like that. It just creates activation records. They're just functions with the same name, right? So remember that the order in which we perform function calls may matter, so please be very careful about this. So that's something that you'll explore more if you play around with some more problems that involve recursion. So I thought I would do an example, just kind of walking you through this process of seeing how one of these call stacks would look. So I'll mention just here that order of calls may matter. So this is just a caution. So let's go through an example here. Previously, we had seen how we recursively could add numbers 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to some positive integer n. So suppose that we were to consider rec sum of 4. So I just want to show you how this would go through, considering that we've seen in a previous lesson, we talked about what this would look like as an actual function. So how would this work? Well, your initial program, when you execute it, you'll start off with the main function, right? So you're going to have a call stack. So here's your call stack. And it's going to have, it starts off by executing main. And then somewhere in the main, it executes recsum 4. So when it calls recsum 4, it passes along. So a part of this, it creates an activation record on the call stack. They'll include the parameters and any of the local variables as they get allocated. And of course the return value as well. And of course it'll tell us where to go when we're done. Right now I don't know what the return value is. But let me walk you through step by step this process. So remember that right now recsum4 is on the top of the stack. So are we going to finish the main function? Not until we're done executing recsum4, right? So to execute recsum4, because it is in fact greater than 1, that means that to answer this question is the same as me asking the following. It's 4 plus recsum3, right? Well, to get the answer to this question requires me to carry out recsum3. So I call recsum3 on that line if you take back and look at that function. Creates an activation record for recsum when we call on recsum3. The input would be 3 in this case. We don't know the return value quite yet, but we have an activation record. Is it going to continue executing recsum4? No, because we don't know the answer to recsum3. It's called recsum3, so now we've created an activation record. Now what's currently going to execute is recsum3. But now recsum3 is going to attempt to answer the question by saying 3 plus recsum2, right? So it's 3 plus this function call. So remember that returns a number, but to complete this operation of this addition, I need the answer of recsum2. So when I'm calling recursively recsum2, so I create a new so it creates an activation record, recsum2, for which its parameter is 2, for n is equal to 2, and we don't know the return value quite yet. So do you notice that I'm not executing any one of these down here, right? It's whatever's currently at the top of the call stack. But now I'm going to call recsum2. So now recsum2 says, okay, well, since n is greater than 1, I get 2 plus recsum1. It's recsum of 1. Well, now notice I'm going to make a function call. So now I'm calling recsum1. The input is 1. Return value, I don't know quite yet. But now here's where it's nice. We have this is the base, this is going to execute the base case, right? So this one here says the answer is 1, so it returns 1. So it says, okay, the answer is 1. So now I'm going to finish. That means just like my plates over here, recsum1 is completed. It's going to be popped off the stack. Then recsum2 is going to be executed. Again, remember it's going to go back to where it was halted at that point. Back to the memory address for which that operation was occurring for completion. So now passes along the 1, pops this, and now this is the top of the call stack. Now I have a 1 plus a 2. So the answer here is 3, right? So this is giving me back the 1. This gives me back 3. Now I'm finished executing recsum2, right? So I pop that off the stack. I give back 3. Because now that's the answer to this. We have 3 plus 3. Well, now 3 plus 3 is 6, right? So I return 6. Pop it from the top of the stack. So we pop the stack. Now I got 4 plus 6. We complete. 10, we return 10. And we pop the stack. And now we're back to the main function call. And for example, if I had a print statement in here, I could print out 10. So this, then of course, when the main function finishes completing all of its operations, this gets popped from the stack and the execution of the program completes. So this is an example of how a program would be executed based on function calls. So the call stack manages which function is currently executing and how we pass along the information or data from one function call to another. And recursion naturally reflects in such a mechanism like this. But remember, this process we just did here with the call stack, it's no different than any other function calls. Just what makes this different is that the functions have the same names. Okay? It's just solving a problem by taking, so I know how to solve a bit of it. I might pass along the rest of it. Sorry, I'm getting really excited here. I'll pass along the rest of the problem because I don't know how to solve it. I'll pass along recursively to somebody else to answer the question. But the point is that how it works, your best friend's the call stack. So just a few things before we wrap up about how this works. Because I just thought I would give you bits of advice about recursion. Okay. So I'll say things to consider. So remember, as I mentioned previously when we first started talking about recursion, make sure you have an appropriate or appropriate several base case. Keep in mind, if you miss a base case, it may be the case that your program will never finish executing. If not, the program may not, or even the algorithm may not terminate, or may be incorrect even. Another thing you need to be aware of is when I have this call stack, naturally on your computer you're going to have a finite amount of memory, right? So the natural question for you is like, okay, well, if I have a finite amount of memory and I have a call stack, can this stack be infinitely tall or as tall as whatever I like? Not always, no, right? Especially it's finite, right? But the point is that there's going to be a ceiling on how many calls you might be able to do depending on how much memory you've got, how much memory is allocated. So keep in mind that if you use too many calls, which causes this call stack to be it's going to be what we would call it very deep. You're going to have what we call deep recursive calls, meaning it's just going to make a lot of calls, making this call stack very, very, very tall. Is if your recursive algorithm uses too much, and I'll put in parentheses around this stack, uses too much memory. Because remember, every time you make a call, it creates an activation record that stores the local variables and all of that stuff too. So if you have a lot of parameters or lots of local variables, that's also memory that gets associated with each one of the calls, right? Remember, each call has its own local variable assignments. So it means that you can't just like jump between calls and use the exact same values that might be stored in there. You'd require a different kind of variable for that to work. But the local variables, each one's tethered to each call, okay? Like each call has its own local variables. Just they take on the values for which that call occurs. Stack memory if your recursive algorithm uses too much memory or never terminates, so I just don't mean that it's just the calls, it's also how much memory you use per activation record too. May never terminate or never terminates, it causes a stack overflow. A stack overflow. So this is when where the program runs out of memory for the call stack. Hence its name. So just please keep this in mind if you decide to use recursion, is that if you know you're going to be making many calls, or each call is going to be rather heavy in terms of the memory usage, in practice you have to be careful about this thing right here, the stack overflow. So if it is a technical issue for you, consider trying to translate into an iterative algorithm that does not use as many calls or potentially less memory, okay? So just as I want to reiterate one conceptual thing to also remember is the recursion should reduce, to a simpler problem or problems, or at least advance computations toward the desired goal. Otherwise, it may never terminate, right? That's a bit of a problem. So another thing I also must stress is that compilers are often designed to be able to optimize recursively written code oftentimes. There's certain kinds of patterns of recursive algorithms that could easily be optimized by a compiler. Though I must stress that often if it's that if you can get away with a recursively described algorithm, that's easy to communicate to other people. But also do keep in mind that each one of those activation records does use memory. So there are kind of trade-offs to consider using a recursive approach. I won't exhaust all of them here, but most certainly those are some things to consider. But yeah, that should give you some ideas of just how recursion actually works. At least hopefully I gave you a glimpse into that. Are there any questions? Any questions at all? Don't be shy. Don't be shy. We're having ourselves a good time here. Don't be shy about asking questions. We have ourselves a blast on over here. While I'm waiting for any questions, I'm going to erase the board here a little bit here. But no, if you're enjoying this content, of course, consider subscribing on Page Wizard Games Learning Entertainment on one of our portals or channels. And of course, if you enjoy this, make sure you tell your friends to come hang on out. We have ourselves a blast over here, learning all sorts of things about computer science. I like to focus a lot on algorithms and theoretical computer science, because that's the stuff, honestly, that's really kind of the bread and butter stuff that really, if you're a computer scientist or you're interested in computer science, or you're a practitioner who wants to use computer science or understand what computer science is about, you need to understand the fundamentals, and that's why this really matters. Also, a lot of that theory is it answers a lot of those why questions. It isn't just simply, oh, this is just because it is. That's not, I don't consider that a sufficient answer. And unfortunately, I find a lot of, I would argue even professors aren't capable of answering those questions because they haven't studied it themselves. Not all of them, but most certainly some. And I think it's important to have some answers to some of those questions, like why is this true or why is that true? And you may not get that full treatment in a course. So I would like to make sure that you have some exposure to a lot of these ideas. And that's one of the main purposes of why I'm here, is try to make it so you can access a lot more of these types of materials that would otherwise either be very difficult to get a hold of during a normal execution of a course, or to enhance your learning, or if you're interested in computer science, you want to learn this stuff yourself, I want to offer you that opportunity to try doing it with yourself, okay? So whether you're in a different area and you're like, oh, I'm interested in math, but I also want to learn a bit more about computer science, everybody's welcome here. That's the point I'm getting at. So whether you're a hobby programmer and you want to learn more about all that algorithm stuff, you're welcome here. Everybody's welcome here. We have ourselves a blast. So again, I also want to mention, just because of the longevity of how long we've been streaming, is that also, if you want access to our notes, that includes the extra example that I've also thrown in here. You can find that on patreon.com/pagewizard. You can find all sorts of rewards there, and that including credits at the end of the videos. That includes, I also sometimes have polls, sometimes I ask for feedback on things. Sometimes I also put out the notes and ask for if anybody has any issues with anything that's there. But also we have a Discord server. That's where, there's not a whole lot going on right now there, but most certainly we have a couple people over there. But I usually try to communicate my ideas over social media and Discord. That way, in case you are looking to watch one of the streams, usually I post just before I go live. Or at least try to give some advance notice. Either way, something to check out. So what I want to do, this is going to be the last part of our lesson, is because we talked about recursive functions, we've talked about recursion as an idea, we've talked about how it works on a computer. I also want to talk about it more from the dreaded M word standpoint, the mayonnaise or mustard. You make a really good sandwich of that stuff. Don't ever discount the importance of mayonnaise and mustard, okay? Sometimes you make a really awesome sub with that kind of stuff. I would like to talk a little bit more about recurrence relations, because I brought that up a little earlier. I would like to talk a little bit more about that. So, namely, I want to talk about it from an analysis of algorithm standpoint. So, for example, if somebody is able to describe to you a recursive algorithm, it's quite natural that they also might describe the number of operations that the algorithm does in recursive terms too. So that's one way you can end up with one of these recurrence relations. So what we're going to do is we're going to talk about how we can simplify these so-called recurrence relations. So I don't see any questions, so let's get on things here. Okay. So imagine you are given, or you derive from the analysis of a recursive algorithm, some complexity function. So this is just a function that represents the number of operations that occur in some scenario, just for our discussion. It may be a recurrence relation, which again is a recursive way of describing a function to somebody, just to keep it simple. So, oftentimes what happens is you get descriptions of some function in a way that's quite a lot like our examples we've seen before. So let me give you an example of what I'm talking about. This is going to be a little contrived of an example at first. So suppose I were to give you this function. It looks like this. For n is greater than 1, where t of 1 is equal to c1, where c1 is some positive integer. So suppose that you're given this complexity function, just for the sake of our discussion here. Notice that it has a recursively defined part, namely this part of the definition, and then it has a base case. So an intuitive way of talking about a recurrence relation like this is you imagine like you're collecting up the non-recursive parts of the quantity. So notice that kind of like some of the examples we have a recursive part, then we add 1. But notice that if I look at every one of these calls here, each one of the recursive cases, each one will include adding 1 every single time. I can imagine I go around collecting up for each one of these calls on a smaller input. It's like collecting up the plus 1s, right? It's like I'm collecting up the waste of all of these calls. Just akin to running through and executing this, just like if it were like the recursive algorithm that it represents for its execution. So each one of the calls produces me a plus 1 until I hit a base case for which I get the C1. So an intuition I want to give you for when we deal with very simple recurrence relations like this one is you can think of it like I'm collecting up the non-recursive work, and I'm collecting those up into a basket, and I want to know how many things are in the basket when I reach the base case. So I would like to derive a relationship that doesn't have any of this recursive stuff in it. And that's what we refer to as solving the recurrence relation. I would like a way of describing the function t without needing to describe it recursively. I would like what so-called we would call a closed form expression. So, just to keep it simple for our example here, I'm just going to get rid of the plus 1. Even though it wouldn't be possible to have an algorithm that does this scenario, because your algorithm will have to perform at least one operation before it does a function call, right? Doing the function call is at least one operation. So I must stress that this is just meant to illustrate the principle I'm going to talk to you about collecting up the non-recursive work of each call. So we're going to use so-called repeated substitution or iterative substitution. These are two names for the same thing generally, or some people call it solving by iteration. We're going to use this technique in the scenario for this example. We'll also do another one, and then we'll see how we can check it. So to apply repeated substitution or iteration, to apply repeated substitution, we write out the definition of t of n, then t of n minus 1. Because remember, it recursively calls on t of n minus 1, right? And t of n minus 1 will call on t of n minus 2. Then t of n minus 2, and so on. And determine how t of n, or how t is computed by writing out a sequence of equations, and finding a pattern. So we're going to try finding a pattern. A good guess. We're good. As humans, we're very obsessed with finding patterns in almost anything. The unfortunate thing is just finding a pattern doesn't mean you found the correct pattern, okay? There could be several correct patterns, but most certainly you can't just say, oh, well, I noticed this pattern, but it doesn't mean it's true always, okay? Especially when we're dealing with the M word, you have to be a bit more careful about it. So, for example, I'm going to write down a bunch of equations so that we can use them. Well, t of n is equal to t of n minus 1, right? And t of n minus 1, that's equal to t of n minus 2, right? And t of n minus 2 is equal to t of n minus 3, and so on. I could keep writing down more equations. And t of 2 is equal to t of 1. And t of 1 is equal to c1. Now, if you're algebraically inclined, you might look at this very quickly and see how I could express t of n. But just for the sake of our discussion, I'm going to go through this carefully. So I want to illustrate the technique. So substitute. So what we're gonna do is we're gonna try substituting each of these equations into each other. Namely, we're gonna start at t1 and work our way up to t of n. Now I must stress that you can work bottom up or top down in this process. I find when you have a recurrence relation like this, you might start at the bottom and work your way up. I find that tends to work pretty decently. But I want to bring the intuition I had with collecting up the non-recursive work into this, just to help you visualize this. Substitute t of 1 into t of 2. Then t of 2 into t of 3. And so you imagine when I have t of n, every time I call on one of these recursive calls, right? I have a recursive call plus some non-recursive work. I can imagine I'm collecting up all that non-recursive work that happens with each one of those calls, plus the initial definitions, the base steps. So I'm going to start off with the base step just to illustrate my point. So t of 2 is just t of 1, right? T of 1 that's just c1. This is what t of 1 is. So when I'm working my way up from t of 1, this is like if I had my bucket here. I'm going to collect up all that non-recursive work. This is c1 right here. This is c1. I put in the bucket. So far I have c1 in here. So now, let's try putting now t of 2 into t of 3. Well, it says that t of 3 is just c1, right? Because that's just what t of 2 is. Right? I have no, there's no non-recursive work on this guy, right? There's none. I'm not adding anything into the bin. T1 did, but that's it. So same thing. This is C1. Because that's just T of 3, right? And I could keep doing this. So I have T of n minus 1 is equal to C1 because that's what T of n minus 2 is. And finally, I could substitute T of n minus 1 back in. I have T of n is just C1. Because that's T of n minus 1. So notice that the total amount of non-recursive work that happens just ends up being what was introduced in the base case, C1. That's how it's totaled up. And you see it's exactly right here. So since C1 is a positive integer, and T n is C1, what does that mean? T is big O of 1. So notice in this case, we only collected up work from the base case. Nothing from any of the other cases, right? So that means that this, if you gave me an algorithm with this, now keep in mind we already talked about that you wouldn't have an algorithm that does this, right? It would never. Now I must stress that the only way this would even work is if you had it where it just executes the base case. Because the recursive case just simply it doesn't make a whole lot of sense to have it where it doesn't have any non-recursive work. But my point stands is that if you gave me that recurrence relation, which I must stress does not have to represent the running time of an algorithm, it's just a function, right? It is big O of 1. So you could take our idea and extend this further if we wanted to. So let's do something a little bit more advanced. Now, do you notice that if I were to have it where we had our first example where I had the +1 before I got rid of it, notice that every time I had one of our equations, it would have added 1 to the bucket each time. So it'd be quite natural to expect that in that case, you should anticipate that each equation contributes something that's a positive integer amount of work every single time you do a call, and there's a linear number of them. So instead of a constant, you might expect something else. I'll let you think about that. So just go through the same example, but instead introduce the +1 that occurs each time. So let's go through another example. So just keep that in the back of your mind with this next example. So the whole idea with iterative substitution or iteration is that we write down a sequence of equations that we hopefully know the conditions for which the base case occurs, so that we have a whole definition of how we compute our function for a given input. And then what we do is we try to substitute by repeatedly applying the definition of each function to each successively smaller part of it, so that we try to gauge and develop a pattern that includes no recursion at the end. So we could do it again from the top, like if you want to start with t of n, like for example from here, you could have seen that I just said, okay, t of n is equal, okay, if that's equal to this, then that's equal to that, then that's, okay, well notice that t of n is equal to t of 1, which is equal to this. So just, I didn't need to go much further than that, right? You also could have worked your top down by just identifying when t of n is equal to t, like when do you actually call t of 1 and how many equations are between there. But you'll notice very quickly that there is nothing else happening except just these calls, right? The point is that you got to think carefully about it case by case, but most certainly you'll find that bottom up or top down, it's sort of analogous to thinking about things recursively like we discussed. Okay, let's do our next example. So this one will actually have stuff that's going to go in the buckets, okay? So consider Gn, or it is g of n minus 1 plus 2n. So this should remind you a little bit of what we had before. I made it a little bit tougher. This is for n is greater than 0, where, let's go with g. I was about to write t, where g of 0 is equal to 1. So we're going to go through the same process, just I really want to illustrate this idea of collecting up the non-recursive work into a bucket, but we all know how that happens, the pattern for which you collect up the garbage, okay? So we apply iterative substitution, where we will write equations for g of n, then g of n minus 1, then g of n minus 2, and so on, to find a pattern. So we're going to go through the same process again. it's usually a good idea to write down these equations, regardless if you're working up or down. That way we have the equations, they exist, at least in a M-word sense, okay? So g of n is g of n minus 1 plus 2n, right? So what's g of n minus 1 then? So we had another equation for g of n minus 1. Well, everywhere where I had n, you have n minus 1. So this is going to be now 1 less. So we have g of n minus 2 plus 2. Remember, it's now everywhere you see an n is n minus 1. And so on. So g of n minus 2 is going to be 2 less. This would be g of n minus 3 plus 2 times n minus 2. So wherever you had the n, you put in whatever that input is. And so on. Until you get the g of 1, which is going to be equal to g of 0 plus 2 times 1. And then we have g of 0 is equal to 1. So when you stare at this, you realize, okay, every time I apply this recursive definition, every time I'm adding something, it looks roughly linear each time, right? So that's a good intuition for where we're going here. So if I start down here, for example, like I did last time, notice every single time when I introduce something into my bucket, notice that every time I start with 1, I put 1 in there, and then I put in whatever that number is times 2, right? Then every time I apply each one of these, whenever I substitute the next equation back in, it's whatever the thing is times 2 I add to the bucket until eventually I get up to g of n. Does everybody understand the main idea? So the whole idea is I want to know how garbage is putting in my bucket, okay? That's what I want to know. That's all I want to know. So let's go through the same process again. Let us substitute the equation for g of 0 into g of 1. Into g of 1. Keep going. Into g of 1. Then g of 1 into g of 2. And we get as follows. So g of 1 is equal to 1, which that is just the definition of g of 0, plus 2 times 1, right? Remember, it's 2 times the something. As long as you remember it's 2 times the something we add into the bucket every time, it's going to be a piece of cake. But what's g of 2? G of 2 is just 1 plus 2 times 1. That's what g of 1 is. You notice I'm just writing it, but there is a little bit of an art to the way I'm expressing this because you want to try to identify a pattern as you keep applying each of these based on the intuition you got from over there from writing out the equations. But what is this being added to? What I add to the bucket, because remember I added 2 times 1 beyond that in g of 1, right? So now I have 2 times the something, which is 2 times 2, right? So what is this actually? This is 1 plus 2 times 1 plus 2 times 2. Do you see anything interesting happening here? Well, let's do it. Let's keep going. Then, now let's substitute g of 2 into g of 3 and g of 3 into g of 4 to see a general pattern. Remember, I'm just trying to guess it. I have to be very careful because if I get it wrong, that's not good, right? This is why we would check our guess once we're done with it. To see a general pattern. So what's g of 3? G of 3, well, we established that that's 1 plus 2 times 1 plus 2 times 2. Well, that's just g of 2 plus 2 times the something, right? Well, what's that? That's 1 plus 2 times, well, because it's 2 times the 1, 2 times 2 plus 2 times 3, right? This is the same as me writing 1 plus 2 times all of this, 1 plus 2 plus 3. Do you see a pattern arising here? Well, let's do another one. G of 4. This would be 1 plus 2 times 1 plus 2 plus 3. This all is g of 3. Do you see how I'm just substituting in where g of 3 would be with what I currently have? And this is the pattern that I'm guessing. This is the iterative aspect of this. Or repeated part. So remember, it's 2 times the something. But that's just 1 plus 2 times 1 plus 2 plus 3 plus 4, right? Do you see a general expression yet? Does it stick out to you quite yet? Well, let's keep going. Okay, so now let's try to give some general expressions. So imagine you keep substituting. So dot, 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 we get to g of n minus 1. Well, what would have been the good guess for this? Well, it's 1 plus a something. It's 2 times 1 plus 2 plus 3 plus all the way up to whatever the thing is, because where did it end? It went up to 1 less than that inside these parentheses, right? So it's n minus 2 right here. So that closes this, that closes that. We need, there we go. So this is g of n minus 2 plus 2 times the something, right? But that's just simply 1 plus 2 times 1 plus 2 plus all the way up to n minus 1. Now, do you see a general pattern now? Does it stick out like a sore thumb now? What was I doing? I was just, remember, every time I took my bucket, I apply one of these equations when I do the substitution. It is just 1 plus 2 times whatever the something is for the input of the equation, right? So each one of them, it starts at n and works its way down to 1. So naturally, if you start from 1 and you work your way up, it should look something like this, right? It should be 1 plus 2 times 1 plus 2 plus 3 plus all the way up to n, right? Now let's simplify. So now this is my guess. This is what my guess is based on using repeated substitution or iterative substitution. So simplifying g of n, or g, we obtain the following. Well, g of n is equal to 1 plus 2 times 1 plus 2 plus 3 all the way up to n. But what is this? What is this? I can rewrite this using a summation. 1 plus 2 times the sum from I is equal to 1 to n of I. So notice that this is 1 plus 2 plus 3 plus 4 all the way up to plus n. So it substitutes each value of I with each one of the terms here. But here's the thing, that has a closed form expression. This is an arithmetic series right here. There's a nice closed form for this. Namely, it'll look like this. N times n plus 1 divided by 2. But notice that this is 2 times half, right? So those two cancel and annihilate each other out. So I end up with 1 plus n times n plus 1. But this is equal to n squared plus n plus 1. But what is that in terms of big O? That's big O of n squared, which matches the intuition we had at the beginning of the example. So we had to double check using our analysis here. I'll say which is. I was about to say where is. Which is big O of n squared. Completing the example. So that's iterative substitution. Now, just as an important remark, is that remember, we're deriving it based on the pattern we're observing, right? We still, if you really just need the check, that requires you to prove something, okay? Are any questions? Any questions? Any questions at all? Because the last thing we're going to do here today is we're going to see how we can actually sit down and prove that what the result we got here is in fact correct. So we're going to try proving that this is in fact correct. So that g of n is equal to n squared plus n plus 1. So we're going to try proving that together. So let me just erase the board on this side. So please just keep in mind that that if you think about it just like you're collecting things up in a bin, especially with these very simple recurrence relations, it's very intuitive to help you out with figuring out what's the pattern. Okay. I'll just recap everything. That way we can talk about checking it. We want to actually check the recurrence relation. Let's see if what we got in the end of this analysis is actually correct. Completing the analysis. Okay, I don't see any questions, so let's proceed. So previously we had shown that that if I give you a recurrence relation, it looks like this. And then we had g of 0, which is equal to 1, right? Okay, so previously we had seen a recurrence relation with this form. That g of n is equal to g of n minus 1 plus 2n when if n is greater than 0, and g of 0 is equal to 1. Now, previously we had used the iterative substitution, or we used iteration to accomplish and obtain this closed form expression for g, which is big O of n squared, right? But we didn't actually check to make sure that it is in fact the case that g of n is equal to n squared plus n plus 1. We just sort of, we observed a pattern by using iterative substitution. So we actually should check this if it's not clear. So a common way to achieve this, and this doesn't have to be the only way, but a very common way of achieving this is using induction. There's different kinds of mathematical induction, but for a recurrence as simple as this, weak induction or just your typical principle mathematical induction will cut it. In fact, just at least for us when we're actually trying to prove the statement. So let's prove we are correct. Let's try to make sure we prove that this is in fact the correct guess. So, as usual with my induction proofs, I'll try to denote a statement for which we're going to perform induction on. In this case, we're going to use n for induction. So let S of n denote the statement. The statement for each n greater or equal to 0 is going to be that g of n is equal to n squared plus n plus 1. I must stress that the left-hand side is referring to that definition over there. So we need to prove that the value you get from this is equal to n squared plus n plus 1. So the first thing we do is we start off with our base step. So here, I'm just going to have one base step. I don't need to go any higher. So we look at S of 0. S of 0 says that we consider g of 0, which is equal to 1. We have to see that the right-hand side here is equal to 1. If we can do that, then S of 0 it holds. By definition, g of 0 equals 1 in the base case. And the right-hand side is 0 squared plus 0 plus 1, which is equal to 1, right? So S of 0 holds. So we've completed the base step. So just remember, we're trying to show that the result of the recurrence relation matches for each value of n is equal to the right-hand side here, n squared plus n plus 1. So this is the base step for n is equal to 0. Now let's do the induction step. So we're going to show that if I presume that it holds for n, then I can show you how it follows that S of n plus 1, or in our case, S of k plus 1, if I assume S of k holds, that it follows that S of k plus 1 holds. Remember, the whole idea here is that since I've established that S of 0 holds, and I give you a mechanism to show that from S of 0 that you can prove S of 1, and that means that you can show that from S of 1 you can get the S of 2, S of 2 to S of 3, S of 3 to S of 4, and it holds for all of them, just like if I was Miss Kitty knocking over a row of dominoes in one line, or helping Miss Kitty climb up a bunk bed. So we're going to show that if S of k, then S of k plus 1. So we're going to fix some k greater or equal to 0. So remember, k, I'm going to start its value is going to be up to at least the highest rung I went to at the base steps in this case. So we're going to assume the statement S of k holds. Which that's the induction hypothesis or inductive hypothesis, which is the following. Which is S of k, which just means that g of k is equal to k squared plus k plus 1. So now we got to show that S of k plus 1 follows from this. And naturally, and the reason why I wanted to show you an induction proof is that you can look at induction and recursion like they're two sides of the same coin. So when I use the induction hypothesis, it'll remind you a little bit of a recursive call. And I find that sometimes when I bring that fact up to students, it sometimes it rings a little bell. So now we show that S of k plus 1 follows where S of k plus 1 is the following statement. G of k plus 1 is equal to k plus, so wherever there was a k before, now it's a k plus 1. So this would be k plus 1 squared plus k plus 1, all in parentheses, plus 1. So when you end up with things like this, where you have an equation that you're trying to establish, A handy way to go about this is just start on one side of the equation and then derive the right-hand side. Or start on the right-hand side, derive the left-hand side. We're going to start on the left-hand side and we're going to derive the right-hand side. So beginning on the left-hand side, by the definition of g of k plus 1, we get the following. Well, g of k plus 1 is equal to, remember this is the recursive part of the definition. Well, if k plus 1 is the input, it's 1 less than that, right? Plus 2 times the something. That's what the recursive part of this, and we can guarantee this, by the way, because k plus 1 would be strictly bigger than 0, right? So that's actually a very subtle detail here. So k plus 1 is bigger than 0, so we use that part of the definition. But what is this? Well, the induction hypothesis says the induction hypothesis says that this is k squared plus k plus 1, right? This is k squared plus k plus 1, right? So I'm going to use the induction hypothesis, replace g of k with that. Well, what's this? That's 2k plus 2. So this is by the induction hypothesis. So you notice how I'm using the induction hypothesis should remind you a little bit of like, I'm just like, okay, I now know the answer to g of k, right? The induction hypothesis tells me the answer. So hopefully that helps kind of connect this a little bit for you. Well, there's some lovely terms here. I'm going to try to get it so I get the form that looks like this. I will tell you that we will get the form that looks like this, but we have to be a bit careful about this. So what I'm going to do is I'm going to rearrange some of these terms. In particular, I'm going to expand out this 2 to make it 1 plus 1. But I could rearrange some of these terms to get the k plus 1 squared, and I could get all the rest of this. So to make k plus 1 squared, what would it look like? Well, k plus 1 squared is k plus 1 plus k plus 1, right? So it's k plus 1 times k plus 1. So you know you're going to need a k squared. You're going to need 1k, and you're going to need 2k's, and you're going to need a 1. So no, fortunately, I have a 2k right here, so I'm going to use that 2k. So I have a 2k. I already have a 1, so I'm going to just hang it. So I'm just going to use this 2k over here. I'm going to hang on to the 1. I'm going to throw this k over here. I'm going to borrow a 1 from this 2, and then I'm left with a 1. So this is by rearranging the terms. But what's this? Well, this is k plus 1 squared. And then I have k plus 1. I have plus 1. But that's the right-hand side, right? Which is the right-hand side, completing the induction step. Completing the induction step. Now that we have this in place, what can we say? We have the base step, we have the induction step. We can use the principle of mathematical induction and complete the proof. It's an important step. We're invoking a theorem here. Therefore, by the principle of mathematical induction, S of n, or S holds, for all n greater or equal to 0. And that completes the proof. So indeed it is the case that g of n is equal to n squared plus n plus 1. Meaning that our derivation via iteration is correct. Pretty nifty, right? So, are there any questions? Any questions about what we did? Any of the steps here in this proof, for example? Or just any broader questions about recursion? Because that's all the main material I had for today. Again, I want to remind you that if you want to get access to the notes from today's live lecture, you can find it on Patreon. You go patreon.com/pagewizard. It's available for supporter access and above. So just keep that in mind if you're looking for access to these notes. There are some additional examples in there. And of course, we have all sorts of fun things over there. But are there any questions? Please don't be shy. Don't be shy to ask any questions. I'm happy to answer any questions. Sorry, I'm just collecting up I'm just putting things in the bucket, okay? I'm having a little bit of fun with everybody. Are there any questions? Any questions? I'm just going to double check the... Just want to make sure I'm not missing anybody. Don't want to miss anybody asking questions. It's rather quiet here today. We had some more people in earlier, but that's okay. So, that being said, if there aren't any questions, I think it's a good place for me to stop here. I want to say thank you so much for coming on out today. It was a blast, and hopefully you'll learn something new about recursion, or if you know about recursion, hopefully some of this stuff helps you out with understanding some more concepts around it, or if you just wanted a refresher. So I want to say thank you so much for coming on out. Again, tell your friends to come out and enjoy the fun with us. Everybody's welcome. And have yourself a beautiful day. I'll see you later.